Welcome back to the Neural Intel podcast. Today, we're diving deep into a core challenge in healthcare technology, fragmented patient data.
hmm
Think about it, one person's complete medical history, but it's scattered across various systems, different clinics, hospitals,
Yeah, it's a real mess sometimes.
and the current ways of piecing this together. Often manual effort, which isn't just slow, it opens the door to errors.
Big time. Simple mistakes can have significant consequences.
So we've sifted through some really interesting research on how cutting-edge language models are being used to automate this crucial process, and we're here to give you the essential breakdown.
Exactly. And the focus of this deep dive is really on the technical strategies these language models are using to automatically link patient records from these different sources.
Okay.
We'll be drilling down into the two key technical tasks involved. First, blocking, which is all about intelligently reducing the sheer volume of potential matches we need to consider.
Right, narrowing it down.
Precisely.
Yeah.
And then matching where the system actually figures out if two records belong to the same individual.
And the research we're looking at uses real-world data.
It does.
Right.
From the Missouri Cancer Registry and Research Center. So we're looking at, practical applications here, not just theory.
Okay, good. So let's unpack this first challenge. Blocking. When you're dealing with massive data sets, multiple institutions, trying to compare every single record with every other record, that sounds computationally impossible almost.
Oh, it becomes prohibitive very, very quickly. The number of comparisons just explodes. Think quadratic growth. That's where blocking comes in. It's fundamentally about efficiency.
Making the problem manageable.
Exactly. Blocking aims to drastically slash the number of record pairs that need serious evaluation for a match. Traditional ways. They might involve exact matches on, say, last name and date of birth.
Or maybe phonetic encoding, like soundex for names.
Yeah, things like that. Or grouping by the same year of birth. But these methods can be quite brittle, They struggle with the messy reality of healthcare data.
You mean like typos, inconsistent formatting?
Exactly. Typos, abbreviations, missing middle names, different date formats. The traditional methods can easily miss matches because of these things.
Which leads us then to this more sophisticated approach, using language model embeddings. How does that work on a technical level for blocking? It's not just keyword matching anymore.
Not at all. It leverages the semantic understanding these models capture. What's really fascinating here is the capability of models like Roberta, which they used in the study, to learn these rich numerical representations, the embeddings of patient records.
Okay.
The basic idea is that records with similar meaning, even if the actual text varies a bit, will have embeddings that are close together in this high-dimensional space.
So it understands John Smith, born Jan 1st, is similar to J. Smith, born 0101, even if the strings aren't identical.
Precisely. It looks beyond just the surface level of text.
So how did the researchers actually apply Roberta to this blocking task? What were the steps?
Well, their main goal was high recall. They wanted to find almost all the true matches.
Okay, minimize false negatives.
Right, while significantly cutting down the number of pairs they actually had to compare. So they fine-tuned Roberta using the sentence transformers library Espert. It's specifically designed for generating these useful sentence embeddings.
And what went into the embedding? What data from the patient record?
They created a consolidated string for each record. It included key attributes: first name, middle name, last name, birth date, and sex.
But they left some things out.
They did. They intentionally excluded social security number and address. Why? Because those fields had really high rates of missing values in their data.
Makes sense. Focus on the more reliable data points. So you have these strings, Roberta generates an embedding for each. Then what? How do you find potential matches?
That's where cosine similarity comes in. It's a mathematical way to measure how similar the direction of two embedding vectors is. Basically, how similar the records are semantically.
Okay, so similar records get high cosine similarity scores.
Correct. And to find these similar pairs efficiently across the two data sets, they use the k-nearest neighbors algorithm, or KNN. They use the AIS library for this, which is super fast for similarity searches.
So for each record in dataset A, find the k most similar records in dataset B based on the embeddings.
Exactly. But just finding the k-nearest wasn't quite enough. They added another step, a cosine similarity threshold. If the similarity score between a pair found by KNN didn't meet this minimum threshold, they just discarded it.
Okay, so KNN finds potential neighbors, and the threshold acts as a final filter. They must have experimented with different values for K and that threshold, right?
They did, and the results showed this really clear trade-off between recall and the number of candidate pairs you end up with.
How so?
When they used lower similarity thresholds, say zero point 0.5 or zero point 0.6, they got near perfect recall, found almost all the true matches, but
But they probably got way too many candidate pairs.
exactly, huge numbers. For instance, at a zero point 0.5 threshold, and K10 meaning the 10 nearest neighbors, they still had around 500,000 pairs to check.
Whoa. Okay, 500,000 is still way too many for the next matching step.
Right, so not efficient enough. But when they raised the threshold to zero point 0.7, again with K10, the number of pairs dropped dramatically, down to about 17,000.
And the recall. Did they lose many true matches?
Hardly any. They only missed 2 true matches at that point.
Okay, that's much better. Did they push it higher?
Yep. They found that a threshold of 0.75, still with K10, seemed like a really good sweet spot. It resulted in just over 4,000 candidate pairs.
Wow, that's a massive reduction. Like 92% fewer pairs than starting from scratch.
Exactly, a 92% reduction. And they only missed 3 true matches. So a very effective balance there.
Minimal accuracy loss for a huge efficiency gain. What happened if they went even higher, like 0.8 or more?
That's where the trade-off really started to bite. The number of pairs kept dropping, sure, but the recall started to suffer more noticeably. They began missing a more significant chunk of the true matches.
So diminishing returns, or even negative returns, past a certain point.
Pretty much. They also found that increasing K, the number of neighbors, beyond 10 didn't really help recall much once they were above a certain threshold anyway.
Interesting. So K10 seems sufficient. Now, this embedding-based blocking sounds powerful, but were there any technical limitations they hit?
Yes, there was a key one they pointed out. It relates to how these models handle minor typos.
The real-world data messiness again.
Right, because language models often use subword tokenization. They break words into smaller pieces.
Like linking might become link and hashtag Tanny.
Exactly. A small typo, even one wrong letter, can cause the tokenizer to break the word up completely differently.
And that would lead to?
A substantially different embedding and therefore a potentially low similarity score, even if the records were almost identical otherwise.
Ouch. So it can be overly sensitive to tiny errors because of the tokenization. That's a critical detail.
Definitely something to watch out for in practice. Data entry errors are, everywhere.
Makes perfect sense. So given that limitation, did they look at any other blocking strategies, maybe combining approaches?
They did. They explored a hybrid approach, combining some traditional rule-based blocking, like maybe exact matches on some fields, with something called the overall similarity score.
Where did that score come from?
It came from their baseline probabilistic linkage method, which they used for comparison. They analyzed this score on their test data and found a really interesting pattern.
Which was?
No true matches had a score below 0.65, and absolutely no non-matches scored a perfect 1.0.
Huh. So that score itself could act as a pretty good filter.
It seems so. They estimated that just using this score threshold could potentially reduce their data set to just over 2,700 pairs. That's a 95% reduction.
Yeah, the recall.
Still 100% recall in their test set based on that threshold. So they highlighted this hybrid strategy as potentially being even more robust and effective for blocking.
Interesting. So maybe the best path forward isn't just embeddings, but a smart combination.
Okay.
That covers blocking. Let's move to the crucial second step, matching.
Right.
This is where this system takes those candidate pairs that survived blocking and makes the final call, same patient or not.
Exactly. And just to be clear, for this matching experiment, they used their labeled dataset AB directly. It was run independently of the blocking experiments we just discussed.
Okay, so they weren't testing blocking and matching together in one pipeline for these results.
Correct. This was purely about evaluating the matching model's performance on known pairs. Obviously, in a real system, blocking output feeds into matching.
Got it. So for this critical matching phase, they threw a bunch of different language models at it, both fine-tuned and zero-shot.
They did a whole range. Roberta, several Llama versions, 3.23b, 3.18b, 3.370b, different Mistral models like Mistral 7b and Mistral Small, and also DeepSeek R1. They wanted to see how they performed when specifically trained for this task versus just using them out of the box.
Okay, quite the lineup. Let's get into the technical setup. How did they configure, say, Roberta, which is more of a traditional classification model?
For Roberta, they fine-tuned it with a standard sequence classification head added on top. They also used a specific input format inspired by a method called Ditto.
Ditto. How did that work?
They serialized each patient record into a string, but used special tokens, like COL before the attribute name, say first name, and VL before the actual value, John.
Haha, clearly marking the structure.
Exactly. Then they'd concatenate the two serialized records they were comparing, using the standard CLS token at the beginning and SEP tokens to separate the two records and mark the end. It gives the model very structured input.
Okay, that makes sense for a classification model. What about the generative LLMs, the llamas and Mistrals? How are they set up? They don't usually have a classification head, right?
Right. For those, they used a prompt-based approach. They basically formatted the two records into a structured prompt that asked the model, do these records refer to the same person? Answer yes or no.
And during fine-tuning?
During fine-tuning, the correct answer, yes or no, was included as part of the target output in the prompt. And to fine-tune these huge models efficiently, they use LoRA.
LoRA, low-rank adaptation. That saves a lot of computation, right?
A ton. It freezes most of the pre-trained model weights and only trains small adapter layers. They also use the unsloth library.
Unsloth. Haven't heard that one as much.
It's specifically designed to optimize training and inference for LLMs, making them faster and use less memory, less VRAM. They even use specific unsloth-optimized versions of some models.
Wow. Okay. So lots of optimization work went into just training these things efficiently. What about actually using them for prediction, the inference stage?
For most of the models, they wanted deterministic output, the same answer every time for the same input, so they turned sampling off, set the temperature to 0.
Makes sense for a classification task.
Yeah, and they used a pretty standard system prompt like, you are a helpful assistant. The only real exception was DeepSeek R1.
How is that different?
The developers of DeepSeek actually recommended not using a system prompt and using a very small temperature setting instead, apparently to help prevent repetition during its reasoning process.
Interesting nuance for that specific model. Okay, so experiments all set up, models trained, or use zero shot. What did the results show? Who was best at matching?
Okay, looking at the fine-tuned models first. Mistral 7B was actually the star performer.
Really? The 7 billion parameter Mistral?
Yep. It had the lowest total number of incorrect predictions, false positives plus false negatives. Llama 3.18b and Llama 3.23b were also very strong, just slightly behind.
And Roberta?
Yeah.
The one sort of built for classification.
Interestingly, Roberta had the highest error count among the fine-tuned models.
Wow. So the fine-tuned generative LLMs actually beat the fine-tuned classification model at its own game, essentially.
It certainly looks that way from these results. It suggests these generative architectures adapt really well to this kind of structured classification task when fine-tuned.
Fascinating. Okay, what about zero shot? No fine-tuning, just prompting the base models.
There, the bigger models generally did better, which isn't too surprising. Mistral Small 24B came out on top. Very few errors, high F1 score.
And the others.
Llama 3.370B was also quite good, close behind Mistral Small, but the smaller zero-shot models like Llama 3.18B and Mistral 7B definitely showed a drop in performance compared to their fine-tuned versions or the larger zero-shot models.
Kind of expected. Zero shot often needs scale. Now, you mentioned DeepSeek R1, the reasoning model. How did it fare, especially on trickier cases?
Right. They specifically tested it on a challenging subset pairs where that probabilistic overall similarity score was between 0.65 and 1.0. These are the ambiguous ones.
The ones that aren't obvious matches or non-matches.
Exactly. And DeepSeek R1 achieved a respectable F1 score around 0.85. But its error count, the number of mistakes, was actually higher than both Mistral Small 24B and Llama 3.370B when they were tested on that same difficult subset.
Huh. So the dedicated reasoning capability doesn't actually lead to better accuracy on the hard cases here.
Apparently not for this specific task. The other large LLMs, without that explicit reasoning focus, performed better on those ambiguous pairs. It was a bit counterintuitive.
And I bet there was a difference in processing time, too. Reasoning usually takes longer.
Oh, a massive difference. Processing that challenging subset took DeepSeek R1 about 26 hours.
26 hours.
Yeah. Whereas Llama 3.370B did the same subset in just 30 minutes.
Wow. Okay, that's not even close. Why is such a huge gap?
The researchers pointed to a couple of things. Reasoning models often generate intermediate thinking steps or tokens, which takes time. Plus, they might need smaller batch sizes during inference because of how they work, slowing things down further.
So the takeaway there seems to be that while reasoning models are powerful for some things, they might be overkill and computationally impractical for large-scale record linkage like this.
Especially since, in this study at least, that reasoning ability didn't actually translate to better accuracy compared to other big LLMs.
It really highlights that cost-benefit analysis you need to do.
Absolutely. The fanciest model isn't always the right tool for the job, especially when you factor in real-world constraints like time and compute budget.
Okay, great. So let's try to wrap this up and pull out the key technical insights for our listeners from this deep dive. What are the main takeaways?
Well, first, I think it's clear that language models show real promise for automating patient record linkage and making it much more efficient than manual methods.
Definitely seems that way.
Second, for the matching part, fine-tuning generative LLMs looks like a very strong approach. They achieved really high accuracy, even outperforming a traditional classification model like Roberta in this study.
Right. The fine-tuned Mistral 7B result was particularly striking. And what about the blocking step?
The embedding-based blocking using models like Roberta can drastically cut down the comparisons. That's the upside. But the downside is that sensitivity to small errors, like typos, because of the subword tokenization.
So maybe not perfect on its own.
Maybe not. That hybrid approach they mentioned, combining some rule-based blocking with insights from probabilistic scores, might actually offer a better, more robust balance of accuracy and efficiency for filtering pairs initially.
Okay, good point. And finally, the lesson from the reasoning models, like DeepSeek.
I think the key insight there is practicality. While these models are incredibly capable in many areas, for large-scale record linkage, the huge computational cost and much longer inference times might make them impractical, especially when other large LLMs achieved similar or even better accuracy in this specific application without that overhead.
So it really boils down to carefully weighing the trade-offs, doesn't it? Model complexity, the computational resources needed, inference speed, versus the actual accuracy required for the specific task, especially in a sensitive area like healthcare data.
Precisely. It's a constant balancing act in applied AI. The most technically complex solution isn't always the most effective or pragmatic one in the real world.
A lot of intricate technical considerations indeed. Fascinating stuff. Thanks for breaking down all those details.
My pleasure.
And for everyone listening, if you want to stay up to date on the latest advancements in research papers in AI and ML, be sure to visit the Neural Intel podcast webpage. You'll find the link in the show notes. Until our next deep dive.